Let's start with a simple question. What happens when something fails in a distributed system? Imagine you're processing a billion records across a large cluster. At that scale, failures aren't unusual. An executor can crash, a machine can go down, or a network connection can fail. Now, here's the interesting part. When something goes wrong, Spark doesn't necessarily need to throw away the entire computation and start from the beginning. Instead, it has mechanisms to recover the data that is no longer available. And one of the key concepts behind that recovery is the resilient distributed dataset, or RDD. So, to understand why RDDs are called resilient, let's first understand how Spark organizes data. So, what does resilient actually mean here? It refers to Spark's ability to recover lost data through recomputation. Imagine that one partition of an RDD becomes unavailable because an executor fails. Spark doesn't automatically need to recompute the entire dataset. Instead, it can trace backward through the lineage and dependencies to determine what data and computation are needed to reproduce the missing partition. That's the basic idea behind RDD resilience. Now, let's step back for a moment. Why does Spark distribute the data in the first place? Well, imagine trying to process a billion records on a single machine. That's going to become a serious bottleneck. So Spark divides the data into smaller pieces called partitions. Those partitions can then be processed in parallel across a cluster, allowing different executors to work on different portions of the dataset at the same time. And that brings us to one of the most important concepts in Spark, the partition. So what exactly is a partition? A partition is the fundamental unit of parallelism in Spark. For a given stage, each partition is processed by a task, and that task runs on an executor. Think of it this way. Instead of giving one machine the entire dataset, Spark divides the work into manageable pieces and processes those pieces in parallel. And there's another important benefit. Because the work is divided into partitions, Spark can recover data at a much finer level when something goes wrong. Why partition-level recovery matters? Let's make that concrete. Suppose an RDD has 100 partitions, and partition 73 becomes unavailable. Do we really want Spark to rebuild all 100 partitions? Of course not. The useful mental model is, one partition is unavailable? Let's recreate only what we need. That's one of the major benefits of dividing the data into partitions. But now we have an obvious question. How does Spark know what it needs to do to recreate partition 73? That's where Lineage comes in. How does Spark know how to recreate a partition? This is where Lineage becomes important. Lineage is the dependency information Spark maintains to describe how an RDD was derived from its parent RDDs, and ultimately from its input. In other words, Spark keeps track of the relationships that led to the data we're working with. So if a partition later becomes unavailable, Spark can use those dependencies to determine what upstream data and computation are needed to reproduce it. And there's a simple analogy that makes this easier to visualize. Think of Lineage as a recipe for data. Suppose you bake a cake and, unfortunately, the cake gets ruined. You don't necessarily need to keep another finished cake sitting in the refrigerator. What you really need is the recipe and the ingredients so that you can make the cake again. Lineage works in a similar way. It doesn't store the actual data as a backup copy. Instead, it maintains the dependency information that describes how the data was produced. So if the required data becomes unavailable, Spark can use those dependencies to reproduce it. That's the basic idea behind Lineage. Now, you might be wondering, when does Spark actually create this lineage? This happens as you define transformations, and Spark's transformations are lazy. So if you write something like filter or map, Spark doesn't immediately process all the data. Instead, it records the relationships needed for the computation. The actual execution happens when you call an action, such as count. At that point, Spark uses the recorded dependencies to determine what computation needs to be executed. So transformations help build the computation, while an action actually triggers execution. At this point, you might be imagining Lineage as a simple straight line, where RDD1 flows into RDD2, which then flows into RDD3. And sometimes it can look that simple. But real applications can be more complex. One RDD might have multiple children, or an RDD might depend on multiple parents, allowing Spark to determine which upstream data is required for recomputation. So rather than thinking of Lineage as just a chain, it's better to think of it as a dependency graph. And that graph becomes especially interesting when different types of dependencies are involved. We'll come back to that shortly. What happens when a partition is lost? Now, let's put all of this together with a simple recovery scenario. Suppose an executor fails, and one of our partitions becomes unavailable. In a narrow dependency scenario, Spark can trace the missing partition back through its dependencies to the specific parent partitions it depends on. It then reapplies the necessary transformations to recreate that missing piece. Notice what's happening here. Spark isn't blindly rebuilding everything. It's using the dependency information to determine what is actually required. Let's break that recovery process down into 6 simple steps. First, a failure occurs, such as an executor crashing. Second, Spark identifies the required data. Third, it traces the lineage and dependencies. Fourth, it identifies the upstream data needed for recomputation. Fifth, it re-executes the necessary transformations. And finally, the required partition is produced on a healthy executor, and the computation can continue. So the important idea isn't that Spark keeps a backup copy of everything. The idea is that Spark has enough dependency information to reproduce what is needed. Now, you might be thinking, why go through all this trouble? Why not just keep another copy of everything? That's a reasonable question. Replication certainly has advantages, but it also comes with a cost. Keeping multiple physical copies requires additional storage and memory, and moving those copies around can increase network traffic. So for intermediate data, lineage-based recomputation can avoid the ongoing cost of maintaining multiple physical copies. But that doesn't mean replication is useless. It simply means Spark has different mechanisms available depending on the situation. Recomputation versus replication. So let's make the distinction clear. Replication means keeping another physical copy of the data. Lineage means maintaining the dependency information needed to produce the data again. Spark can use both approaches. For example, persisted RDDs can optionally use replication, while lineage-based recomputation is fundamental to recovering derived RDD data. And shuffle data has its own recovery mechanisms. So it's not really a question of replication versus lineage. They're different mechanisms that address different recovery needs. RDD, partition, and lineage. Let's pause and connect the 3 concepts we've covered. The RDD is the distributed dataset. The partition is the portion of that dataset processed by a task. And lineage is the dependency information that helps Spark determine how a lost partition can be recomputed. Put those 3 together, and you have the foundation for understanding RDD-based recovery. RDD and Spark fault tolerance. There's one important clarification here. Lineage is not the entire fault-tolerant system in Spark. It's one important recovery mechanism within that larger system. Spark also has mechanisms such as task retries and other ways of handling failures. Lineage provides the dependency information Spark needs when recomputation is required. So think of Lineage as an important piece of the larger fault tolerance picture, rather than the entire picture itself. And this leads to an important limitation. Lineage is not a backup. It doesn't contain a backup copy of the data. It contains the dependency information Spark can use to reproduce the data. And depending on the dependency chain, recomputation may ultimately require Spark to read from the original input. So Lineage can tell Spark how to reproduce the data, but it doesn't eliminate the work required to actually reproduce it. That's an important distinction. So let's put the entire mental model together. We start with the input. Spark represents that data as partitions. Transformations create new RDDs, and Spark tracks the dependencies between them. Now imagine that some required data becomes unavailable. Spark can trace back through those dependencies and re-execute the necessary computation to produce the missing data. That's the basic recovery model we've been building throughout this section. So why is it called a resilient distributed dataset? Let's break the name down. Distributed because the data is divided into partitions that can be processed across machines. Dataset because the RDD represents a collection of data. And resilient because Spark can use Lineage and other fault tolerance mechanisms to recover from failures. Once you understand those three words, the name RDD starts to make a lot more sense. So we've now built the basic mental model. We know what an RDD is, we know what a partition is, and we understand why Lineage is important for recovery. But we've deliberately kept the dependency graph fairly simple. Real Spark applications can have much more complex dependencies. So next, we're going to look at what Lineage actually contains, how dependencies are represented, and how Spark uses those dependencies during recovery. And then we'll connect that Lineage graph to the actual execution of a Spark application, the DAG, stages, and tasks. That's where the picture gets much more interesting. Welcome to the Lineage Deep Dive.